Hello, hello, welcome today for our lesson 2 on timber design to BS 5268. So today we are going to look at an example of a timber beam which is made of timber. I'll read: a timber beam with a clear span of 2.85 meter supports a uniformly distributed load of 10 kilonewton, including self-weight of the beam. Determine a suitable section for the beam using timber of strength class 16 under service class 1. Assume that the bearing length is 150 millimeter and that the end of the beam are held in position and compression edge held in line. So that is our question. We have to determine a suitable section for the beam using timber of strength class 16 under service class 1, assuming bearing length of 150 millimeter and that the end of the beams are held in position and compression edge held in line. So we'll go to solution. Now, step number 1 in solution, we have to sketch and visualize how the beam is carrying the load. Now, remember, looking at this particular point, these are the bearings of 150 millimeter length at both ends of the beam. Then you have a uniformly distributed load. Now, be careful. This is 10 kilonewton, not 10 kilonewton per meter. However, it is uniformly distributed. Now, from the procedure of design, timber design, we said first step is to calculate the effective span. And where effective span is the distance between centers of bearing. So effective span L will be equivalent to, now it will be equivalent to from a half of this support on our left hand side to a half of this support on our right hand side, meaning that from here, this will be now, because of 150 is from here to here, now it will be 75 millimeter. Now 75 millimeter plus 2,850 millimeter plus another 75 millimeter to the center of the support on the right hand side. So you find our effective span will be 2,850. I'm sorry, this is 2,850 plus 150 divided by 2, meaning a half to the halfway of the support plus 150 over 2 to the halfway of the other support or bearing, giving us 3,000 millimeters. So this is our effective span. Now, from effective span, we go to, now procedure number 2 is grade stress and modulus of elasticity. Now, remember here, the most important thing here, they said our timber is class 16. Now we are going to the table and obtain the grade stresses and modulus of elasticity from the class C16. Now the things you have to obtain is bending stress parallel to the grain, shear parallel to the grain, compression perpendicular to the grain, and the modulus of elasticity. Now, because this beam is acting alone, is only one member, we shall use the modulus minimum, E minimum meaning the lowest value. Now, I'll open the table. Now, let me demonstrate how we read the value from the table. So I'll come to my table here. So this is my table. So here we have strength class C14, C16, C18, and C22, C24 up to D70. But now our question told us that ours is strength class C16. So I'll move along this C16. So you find that bending parallel to the grain is 5.3 Newton per millimeter squared. So this is the first value, 5.3 Newton per millimeter squared. I hope you can see. Then I'll go to another value is compression perpendicular to the grain. So we are having two values, the value of 2.2 Newton per millimeter squared and the value of 1.7 Newton per millimeter squared. And now we said, because the question doesn't tell us if when is a defect has been prevented, so we have to use the small value. So we are not taking 2.2 Newton per millimeter squared because the question didn't specify if when was prohibited from occurring. So under compression perpendicular to the grain, we shall adopt the smaller value, which is 1.7 Newton per millimeter squared. Now, shear parallel to the grain is 0.67 Newton per square meter. And then we go to modulus of elasticity. Now, because the beam is a single beam, we use the E minimum, meaning the E minimum means the lowest value, because you have E min to mean average and E minimum to mean the lowest value. So from strength class C16, you find that E minimum will be equivalent to 5,800 Newton per millimeter square. So we have obtained the properties from, now remember this table is found, these values are found in table 8 and table 9 of BS 5268. So after we obtain them, so these are the values we have. Bend parallel to the grain, we saw it 5.3. Shear parallel to the grain, we saw it 0.67 per millimeter square. Compression perpendicular to the grain, we saw it as 1.7. Now there were two values. It was 2.2 Newton per millimeter squared and 1.7 Newton per millimeter squared. But now we said we take the small value of the two because the question didn't tell us whether then that weakness or that defect has been prevented from occurring. Then modulus of elasticity, we take E minimum because it is only one single beam, which is 5,800 Newton per millimeter squared. Now, the third step is modification factors. Now, remember our beam is in service class 1. Now, we said for you to use service class 2, moisture content factor, which is K2, it means the timber should be used in service class 3. But if it's used in service class 1 and service class 2, we don't require K2. That's why we say now K2 does not apply since the beam is subject to service class 1. Okay, now K3, because they didn't tell us the duration of loading, remember K3 is the K factor for load duration. So we assume it is a long-term load duration, and long-term load duration has a value of 1. Then now, K8 is load sharing ratio. Now, K8 is only used when we have more than one beam. Like it means beams are sharing the load being applied to the beam system is being shared. But here we only have one beam, so K8 is not relevant. So we say K8 does not apply since there is only one single beam. Now we move to depth factor, which is K7. We said that now, first thing, what we are going to assume is that now we assume our timber section, our timber beam has a depth of 250 millimeter. Now, from the definition, we said if the thickness or depth lies between 72 millimeter and 300 millimeter, we use our formula K7 is 300 over H power 0.11. Because we are assuming our depth is 250 millimeter, now we shall use the formula. Now remember, because we are assuming our depth is 250 millimeter, when we go to the section, standard section table, you must ensure you use a depth of 250 millimeter to conform with your earlier assumption. I will show you how to go about it. Now, if I calculate from the calculator, if I substitute H with 250, I find like my K7 will be equivalent to 1.020. Now, and after finding the K factor, now we go to bending. Now, in bending, we start with design moment. Like I told you in the previous lecture, I told you that design moment refers to moment which is brought about by the external loads being applied on our beam. We know that for uniformly distributed load, moment is WL squared over 8. But now our case here, now if W is in kilonewton per meter, but our W is in kilonewton. So because it's in kilonewton, we only have WL. So this is capital WL over 8. But if it's a small w, meaning kilonewton per meter, then we use WL squared over 8. So I replace my W is 10 kilonewton, I multiply by 3, which is effective span, 3 meter divided by 8, I get is 3.75 kilonewton meter. This is our design moment. Now, from there, we go to permissible bending stress. We said when you have ADM, it means permissible, then these two vertical lines means parallel to the grain. First of all, remember we have assumed our depth, our H is 250, so it will be given by this stress. This one here is bending stress parallel to the grain, but obtained from our table. The table I showed you, so this 5.3 obtained. Now I multiply by only K3, which is load duration, times the depth factor, which is K7. So here we are only using K3 and K7. So we get is 5.406 Newton per millimeter squared. Now, remember we said we have design moment and moment capacity or moment of resistance. So moment of resistance, we said, is now the capacity or the ability, the moment the timber section can carry without failure. Now, we know that moment capacity is given by as a product of permissible bending parallel to the grain multiplied by the section modulus. Now, at this particular point, we now assume it is at the worst situation whereby our design moment is equivalent to the moment capacity, meaning that my permissible bending stress parallel to the grain times my section modulus is equal to the design moment. And now you divide here by permissible bending, you divide here by permissible bending, but now we say it should be at least equivalent or greater than the design moment. So when I substitute now 3.75 design moment, we have it here, but now we multiply by 10.6 to convert it from kilonewton meter to Newton millimeter. Why? Because our permissible bending stress is in terms of Newton per millimeter square. So for us to have a uniform unit, we have to ensure our moment is in Newton millimeter. So to convert kilonewton to millimeter, we multiply by 1,000, which is 10 power 3. And also to convert from meter, this meter to millimeter, we multiply by 1,000, which is 10 power 3. So the 10 power 3 and 10 power 3 give us 10 power 6. So now when we divide these, you find like it will be 694 times 10 millimeter cube. So this will be our ZXX. This is the section modulus. Now, you have to keep this one here. So when we go to the type of property, we look at a section with a depth of 250, but which ZXX, so section modulus along XX axis, is slightly above this value here, which is 694. Now we'll move to deflection. Now we know that, as we said, permissible deflection, which is delta P, is given by 0.003 times span. This is a standard formula, 0.003 times the effective span of the beam. So deflection occurs due to bending and due to shear. But now you find that the deflection due to shear is likely to be insignificant in comparison to the bending deflection. Now we say like bending deflection accounts for more than 90% of deflection. So shear deflection only contributes to about 10% of total deflection. So in our first attempt, we are going to assume the shear deflection and assume that the total deflection is as a result of the bending deflection. So now that we say total deflection, remember this formula here is for bending deflection. Since we say like bending deflection accounts for 90% of total deflection, now we have assumed that shear deflection is 0. So I'll come here. Now I'll come here and substitute. Now 5 is a constant. I take 5 times. Now 10, remember 10 here is W in kilonewton, but now I convert it to Newton. That's why I raise it to power 4. So 10 power 4 Newton and not kilonewton. And then remember this L effective span is 3 meter, which is I can write as 3,000 millimeter cubed divided by 384 is a constant. Then you have E mean. E mean is modulus of elasticity obtained from the table of the section. We obtain it together with the grade stresses. Then now IXX is second moment area, which we don't know. Now this is our missing component. We want to estimate the value of IXX. So I'll substitute total deflection from the formula 0.003. I multiply by 3000. This is now 0.003 times span should be greater, because this one is permissible. At once it should be equivalent to total deflection, but it should be greater than that. That's why we are using equal or greater than. So 5 times 10 power 4 times 3000 cubed divided by 384 times 5800 times IXX. Now, if I make the IXX the subject, you find that I get IXX will at least be equal to 67.3 times 10 to the power 6 millimeter power 4. Like the minimum value is 67.3. Now, remember, I have two values. I have IXX of 67.3 and I have ZXX of 694 times 10 millimeter cube. Now, when I go to the table of section property, I look for section with ZXX greater than this and IXX greater than what I have calculated. And now, but now remember we said the depth of our section is 250. So when you go to the table, ensure you only look at sections with a depth of 250. So 250 is fixed. We cannot move away from it. So I'll come here, I'll come to the table. So we go to our table. We go on page 10. So this is our table here. Now, remember, we have these. This is our table now. We have a section now, what we call customary size. I mean, like, now here we have 100, 100, 150, 175, and 200 and 225. So we cannot use this first set. Why? Because the depth, we don't have a depth of 250 millimeter. The minimum depth is 100, the maximum depth is 225. So we cannot use any section here. So we'll move to the second set, which is now 47 up. This second value are our depth. So I have a depth of now 250. Remember, when I use the depth of a h of 250, I must restrict myself to 250. So when I come to this section here, I'll try to compare the value. The first value is for area. This is area. This section modulus. Now, this is now the Z. So what we use is Z along XX. So when we talk about ZXX, it means just about the X axis. So we only use the Z along the Z axis, and IXX is what we call second of moment area. We also use it along the XX. Now let's go back here. We found that our ZXX was, our ZXX, I'm sorry, is 694 times 10 power 3 millimeter cube, and our IXX is 67.3 times 10 power 6 millimeter power 4. So we are going to look at a section which has value greater than that. So when we come back to our table, you find like where we have 250, this value here, ZXX is 490. Now for 450, because we are considering the 250 depth, now 490, and our ZXX we calculated was 674. So we disqualify, this section is not suitable. So we'll move to another section. Now we move to 63 by, now 63, it only has 150 millimeter depth, 225 millimeter depth. So since we don't have a 250 millimeter depth section, we don't use any section from 63. Now, next is 75. So 75, but now we only focus at 250 because it's the depth we use to calculate the depth factor. So when I come here, this section 250, 75 by 250, I find like my ZXX is 781, which is greater than calculated, okay. Then now I'll check my second moment area, which is IXX, which is 97.7, which is greater than my calculated value. So I'll be convinced that section 75 by 250 is able to fulfill those two conditions because the ZXX and IXX are both greater than what I have calculated. So now from there, I will obtain the value of area. Our area is 18.8 times 10 to the power 3 millimeter squared, and obtain this value for ZXX of 781 and IXX of 97.7. So we can go back now and say, now from table 6.8, now you find that section 75 times 250. Now this 250, we must use it. Why? Because in calculating our K7, we assumed our section depth to be 250. So provide ZXX, now we read from the table, which is 781 times 10 to the power 3, IXX of 97.7 times 10 to the power 6 millimeter power 4, and area, this area we saw it 18.8 times 10 power 3 millimeter square. Now remember, the value you take from the table, you see we calculated 67.3, but now our value is 97.7. Like the value from the table should be more than what we calculated. So we can now conclude and say, hence total deflection, including shear deflection, can now be calculated by, now remember in the first case, we said because shear deflection contributes to only less than 10% of total deflection, we assume it is 0 and calculate deflection due to bending only. Now we have to come here and include the shear deflection. So these are formula. You find that bending deflection is this one here, 5WL cubed over 384, E minimum IXX, and then bending due to shear is 12 WL over 5. This is 5 constant. E minimum modulus multiplied by the area. So I'll substitute 5 times W is 10 kilonewton, you change to Newton, times span cubed divided by 384 times 5,800 times 97.4 times 10 to the power 6 plus, now this is due to shear. So when you look at it, imagine bending deflection is 6.2 millimeter, while shear deflection is 0.7 millimeter. So basically meaning shear deflection contributes to about only 10% of total deflection. So my total deflection will be equivalent to 6.9 millimeter. Now, but now our permissible deflection is 0.003 times 3,000, which is effective span, which is 9 millimeter. Since 6.9 millimeter is less than permissible 9 millimeter, we say a beam with the 75 times 250 section is adequate for bending and deflection. So bending and deflection criteria has been passed. Why? Because the value of deflection obtained is less than what is permitted. So if you want to see deflection formulas, I can show you here. Now, this way we obtain deflection formula. So we have the deflection here formula. Maybe if we have a uniformly distributed load is 5/84 times WL power 4 by EI. Now, what I want to help you is that now, if W is small w, when it is in terms of kilonewton per meter, or rather, when W is in force per unit length, you use L power 4. So the W will be in terms of maybe kilonewton per meter. But now, if W is in kilonewton, in kilonewton, like this case here, now it will be WL power 3, not power 4. Power 4 only comes if W is per meter, yeah, like per unit length. So kindly get the difference. I'm saying if W is in kilonewton, is a uniformly distributed load in terms of kilonewton per meter, use WL power 4. Even here you see it's WL squared because W is kilonewton per meter. But now if W is just kilonewton, now we use WL power 3. Now if it's a point load at the center, then we use also now WL. We reduce it from L squared to L because W is just kilonewtons. Okay, let's proceed. So from there, now we go to lateral buckling. Lateral buckling. So first of all, we say that permissible, what is allowed? Permissible, now depth over breadth should be equivalent to 5. This is from table 19 of BS 5268. So let me show you table 19 now, lateral buckling, what you mean by lateral buckling. So is here. So this is the table I'm talking about. It talks about maximum depth to breadth ratio. So table. Now, if you want to see it well, you can go to table 19 of BS 5268, the code that is guiding us in our design. So this is the table about lateral buckling. So let's continue. So you find like permissible is D over B. Now remember our section was 75 times 250. So this, the first value is our breadth, B, and our second value is our depth D. So permissible here is, now permissible is 5, but now our actual is D. Our D is 250, like I say, is 250. And now our B is 75. So when I divide 250 over 75, I get 3.3, which is less than permissible. Permissible is 5, like the maximum allowed is 5, but our section gives 3.3. So we can say hence section is adequate for lateral buckling. What we mean is that lateral buckling will only occur if D over B is greater than 5. But if it's less than 5, then lateral buckling will not occur. So let's go to shear. Now, permissible shear is, we said permissible is what our timber section can withstand, can carry. So permissible shear is now shear ADM is equivalent to shear G. This one is what we obtained from the table. We only multiply by the load factor. It was 0.67. We multiply by 1. So you find 0.67 Newton per millimeter square. And then we'll go to maximum shear force. Remember, maximum shear force here, this is a symmetrical beam. FV will be equivalent to RA, which is equivalent to RB, which is equivalent to W over 2. Now, W is 10 kilonewton. I just multiply it by 10 power 3 or by 1000 to change it from kilonewton to newton. Then I divide by 2 because remember RA is equivalent to RB and it's W over 2. So it will be 5 times 10 power 3 Newton. Maximum shear stress at neutral axis is, now we have a force. We know that to find a stress from force, you divide force by area. Now, from the last presentation, we said like for rectangular section, the maximum applied shear is equivalent to 3 times shear force divided by 2 times area. Now shear force, we have it here. Remember the area is what you obtain from the table of section property, geometrical property. So this is 3 over 2 times 5 times 10 power 3, which is now our maximum shear force divided by 18.8 times 10 power 3. Remember this 18.8, we obtain it from the table where we got IXX and ZXX. So this will give you 0.4 Newton per millimeter squared. Now apply the 0.4 Newton per millimeter squared. So our permissible was 0.67 Newton per millimeter squared and our applied is 0.4 Newton per millimeter Newton per millimeter square. Now, since applied is less than the permissible, we say the section is adequate in shear. It means it will be able to overcome the shear from applied load because its capacity is 0.67, but the load only subjected to 0.4. So let's go to bearing now. Permissible bearing stress. Permissible, remember, which is a permissible compression. C, ADM means permissible. Now this perpendicular, this line here, this horizontal and vertical line means perpendicular. So it's equivalent to, now this one is what we obtained from the table. And remember, this compression stress, there were two values and we took the lower value. Why? Because we said we are not sure if the vein, that defect is prohibited from occurring. So it was 1.7, I multiply by K3, which is a load duration factor, which is 1, you get 1.7 kilonewton per millimeter, Newton per millimeter squared. So end reaction F, now end reaction F is just equivalent to RA, which is RB, which is given by W over 2. Our W is 10 times 10 power 3. To change it to Newton, I divide by 2, I get 5 times 10 power 3 Newton. Now, I go to compression stress applied. Now, A means applied compression stress perpendicular to the grain will be the end reaction F divided by the breadth of section times length of bearing. So, which is 5 times 10 power 3 divided by, remember our section is 75 times 250. So, that's B is 75. But now, from the question, we were told that on bearing of length 150. So LB means length of bearing, which was 150. Remember when we are calculating effective span, we had 150, whereby we take half of 150, and added to 2850. So these are the lengths of bearing. So I get 0.44 Newton per millimeter squared. Now, applied is 0.442 per millimeter squared and permissible is 1.72 per millimeter squared. Permissible is very, very much bigger than applied, so the section will be able to withstand bearing. So we say, now we will come and conclude, hence the section is adequate in bearing. You say, hence the section is adequate in bearing. Why? Because permissible is greater than applied. So then now the general conclusion we say, since all the checks are satisfied, use 75 millimeter times 250 millimeter, so on C16 beam. Yeah, because you are testing whether C16 beam is suitable. So you conclude, use C16 beam. Thank you very much for your time. Let's meet for another example on timber design.